In this video, we are going to study about local field or internal field or Lorentz field. Okay, and also Clasius equations. Okay, now let us see what is the local field or Lorentz field. In dielectric solids, the atoms or molecules experiences not only the external applied electric field but also the electric field produced by the dipoles. That means there will be a internal electric field generated by the dipoles, which we are separating by using a field. So the resultant electric field acting on the atoms or molecules of dielectric substance is called local field or internal field. That means some internal field is generated. So we are going to study about that internal field or local field. When a dielectric is exposed to electric field, then polarization takes place. Due to this polarization, different sets of dipoles are formed in the dielectric material. So the total electric field present on an atom is known as, that means considering only one atom, that the total field, entire electric field present on an atom is known as internal field. Okay, see. So we are considering the dielectric materials, and there is a spherical cavity, and at the upper end there is a positive charge and the lower end there is negative charges. How the distribution of charges will be around the nucleus, see here. Okay, so consider a dielectric material in the electric field. We are applying the field in a direction of intensity E between the capacitor plates so that the material is uniformly polarized. So to apply the uniform polarization, we are considering the capacitor plates so that a material can be placed between those two capacitor plates. So to equally maintain the polarization throughout the material. So as a result, opposite type of charges are induced on the surface of the dielectric near the capacitor plates. So positive charge, negative charge, and positive charge inside, and at the plates there is a negative charge. So the local field is calculated by using the method suggested by Lorentz. Hence this is also known as Lorentz field. Okay, according to this method, consider a small spherical region of the dielectric with an atom at the center of the sphere, for which the local field is to be calculated. So we are considering a small region for this entire purpose. The radius of the sphere is large compared with the many molecules but small compared to dimensions of the whole dielectric. Okay, if the dielectric is placed between two capacitor plates, the electric field experienced by a molecule of dielectric. So the dielectric field at the center of the sphere may be written as E local equals to, there is a 4 fields generated by this, E1 plus E2 plus E3 plus E4. Let us see what are those 4. Field E1. E1 is the field intensity at atom A due to the charge density on the plates. From the field theory, E1 equals to d by epsilon naught. So where d equals to P plus epsilon naught into E. So we are replacing the d value here and getting E plus P by epsilon naught. That is the field E1. And field E2. E2 is the field intensity due to the charge density, that means due to the polarization induced on the two sides of the dielectric. So E2 equals to minus P by epsilon naught. Field E3. So is the field intensity at A due to all the dipoles of the atoms inside the spherical region. So how many number of atoms that should be present inside the particular spherical cavity, spherical region, that field is E3, that is the other atoms contained in the cavity. So we are considering a small region. Now we are assuming a cubic structure when it is. So E3 equals to 0 because of symmetry. Okay, if the structure is cubic, then E3 is a 0. E4. So E4 is the field at a point A due to the polarization charges induced on the spherical surface, and it is calculated by Lorentz. So finally, so there are four fields. Okay, so let us consider a spherical cavity. The enlarged view of the imagined sphere is shown in figure. The enlarged view of an imagined sphere. So we are considering a spherical region. That spherical region is to be assumed like this. If ds is a small area of an area element on the surface of the sphere of radius r, making angles between theta and theta plus d theta, where theta is the direction with reference to the direction of the applied force. Okay, so we are considering a small area ds. Then the area element ds equals to 2 pi into pq and qr, theta plus d theta. Okay, so from triangle APQ, sine theta equals to, what is sine theta? PQ by R, which is the radius, and PQ equals to R sine theta. Okay, PQ equals to, the value becomes R, so that is a R sine theta, small r. So opposite by hypotenuse. Okay, so this is the hypotenuse AQ, that is the hypotenuse value, and PQ is the opposite face. Okay, so from sector AQR, d theta equals to QR by R. This is equal QR equals to R d theta. So substituting these in equations, in the above equation, so ds equals to 2 pi into R sine theta into R d theta. Now ds becomes 2 pi R square sine theta into d theta. So now the charge element dq on the surface ds is equal to the normal component of polarization multiplied by the surface area. Now dq is a charge at ds surface area. So dq equals to p cos theta into ds. Now dq equals to p cos theta, and we are substituting the ds value here. Now the total become p into 2 pi r square sine theta cos theta d theta. Now the field due to this charge at A, denoted by dE4 in the direction theta equals to 0 is, so dE4 equals to dq into 1 into cos theta by 4 pi epsilon naught into r square. It is this equation becomes in the early stage of this chapter, that becomes the square of the distance and one of the product of one of the charge. Do you remember that? Okay, so dE4 equals to p into 2 pi r square sine theta cos theta into d theta by, that means we are replacing the dq value, and again here is a cos theta value. Okay, so p by 2 epsilon naught, so pi r square gets cancelled, so sine theta cos theta, and here also another cos theta, right? So cos theta becomes cos square theta. Okay, yeah, we are going through this. And next, so there is a total field at E4 due to the charges on the surface of the entire cavity that is obtained by integrating the surface element is a ring. So the limits of integration with respect to theta are from 0 to pi. So integral dE4 equals to, we are integrating the field due to field E4. Okay, now the term becomes, okay, minus P by 2 epsilon naught into minus cos theta, that becomes cos cube theta by 3 into 0 to pi. Okay, so minus P by 6 epsilon naught into minus 1 minus 1. We are substituting the values pi upper limit minus lower limit. Okay, so now the total equation becomes P by 3 epsilon naught. So this, the local field equals to E plus E4. So now local equals to E plus P by 3 epsilon naught, the total becomes. So it should be observed that local field is greater than the applied electric field. So the local field is a strong field, that is greater than the applied electric field. Okay, so now let us see the Clasius-Mosotti equations. There is a relation between these two. So after the Lorentz field, we are continuing this. Okay, now the relation between the dielectric constant and the polarizability of the polarized dielectric. Come again, the relation between the dielectric constant and the polarizability of polarized dielectric is known as Clasius-Mosotti equation. So let us consider the elemental dielectric having cubic structure. Since there are no ions and no permanent dipoles in these materials, so the ionic and orientational polarizations are 0. So except electronic, these two becomes 0. So hence polarization equation is, okay, so that is a local field equation EL. We are substituting that here, and P into 1 minus n alpha E by 3 epsilon naught equals to this side, and n alpha E becomes this side. Now the polarization P will be this term. So we know that polarization according to permittivity of free space, permittivity and permittivity for specified medium or relative permeate. So now the equation is comparing with this. So by solving this, we have the equation finally E epsilon r minus 1 by epsilon r plus 2 equals to n alpha E by 3 epsilon naught, where n is the number of molecules present per unit volume. So this relation is known as Clasius-Mosotti equations.